I'm Tigran Kremian from FINRA. I'm here to talk about what big data means at FINRA and what technologies we use to solve some of the business problems at FINRA. Specifically, I'll go over how we use Hadoop and HBase as a graph processing tool to reconstruct stock market events. And also I'll go through some of the lessons learned of running a large, persistent, petabyte scale HBase cluster on AWS. About me, I'm the VP of Data Platforms at FINRA, responsible for big data ingestion and processing at FINRA, as well as big data management. You can reach me via email, or I have a pretty unique name. You can find me on LinkedIn. So, as many of you know, stock market is a vital part of U.S. economy. Billions of shares exchange hands each day when sellers and buyers trade equities on the stock market. No matter how big or small those transactions would be, FINRA is there behind the scenes to make sure that markets are fair and the investor is getting the fair price. FINRA stands for Financial Industry Regulatory Authority, and it is our responsibility to oversee activities on the stock market. We are a very mission-driven company, and our mission is investor protection and market integrity. So FINRA processes 33 billion market events daily to help us monitor U.S. financial markets. We oversee close to 4,100 firms. These are investment banks, and approximately 620,000 individual brokers who trade securities in the stock market. Our big data footprint is roughly 2 petabytes of online storage and another 6 petabytes offline data stored on tapes. So to form a holistic view of the events that take place on the marketplace, FINRA gets data from different sources. We get trading data from banks, from exchanges, as well as trade reporting facilities and other sources of data. Now, just to give you a sense how big the data is, Citi is a big company. It has a big data problem. We get all their trading data. Goldman Sachs is a big company. We get all their trading data. In fact, we get trading data from all banks that trade equities in the United States. NASDAQ is a big company. We get all their trading data. We get trading data from NASDAQ, from New York Stock Exchange, from BATS, from DirectEdge, who recently merged with BATS, as well as trade reporting facilities. These facilities are used to disclose transactions, the trades that take place off public exchanges. Once we get all that sea of data, we look for basically issues that reveal compliance issues, that have anything to do with fraud, market manipulation, as well as other forms of market wrongdoing. An example of a compliance check could be completeness and timeliness of data submitted to FINRA. Say, firm A sends data, reports that they send data to firm B, and when we look at firm B data, we don't see those events. That can trigger a compliance alert. A classical example of fraud is an insider trading. Happens when people trade with non-public information about stock. An example of market manipulation would be front running. Happens when you're about to buy certain shares of stock and somebody gets in front of you, executes, and you no longer have that price point for you to execute your trade. So there are many other patterns that we look to mine the data and find issues with market wrongdoings. In fact, my colleague later on today is going to talk more about some of those issues that we find, and feel free to, if you're interested in those and how business uses that data, feel free to attend his session. So just to give you an idea, what happens behind the scenes? I realize I have a pretty complicated title on my presentation, Market Order Flow Reconstruction. So what happens behind the scenes is many different things. Let's say you go to your favorite broker site, be that Ameritrade, be that E-Trade, Schwab, or whatever that might be, and you put an order to buy 35 shares of IBM, you click buy, you get a confirmation that your order has been filled. Several things can happen. I need to learn how to press the button. First of all, if the broker-dealer that you're trading with has that stock in their inventory, it can internally fill that order. Pretty simple. If the broker-dealer does not have inventory, it will forward that to an exchange when buyers and sellers are met. Oftentimes, what we see happen is a particular order gets split, and it's been sending to multiple exchanges, multiple firms, or dark pools. Dark pools are private exchanges where institutional traders are trying to execute bulk securities. They do that off the public exchanges so that they can guarantee their price point. If they don't do it in a private setting, if they show that they have an intent to execute bulk, their price point will move and they won't get their price. Let's not forget high-frequency traders. High-speed, sophisticated computers. Their goal is to collocate as closely to exchange trading platforms as possible, because laws of physics really plays into when you execute in microseconds. When we look at their data, they really create whole skew of data. When we look at those, we see millions of routes, millions of cancels each day. What they're trying to do is they're trying to put multiple orders into the stock market, either to check the price, what's happening on the market, and if no one from the other side, the algo or another high-frequency trader comes and executes against that order, they quickly cancel them and they zero out their order book for that day. At the end of the day, when we look at the data, we see pretty complicated network, a graph of events that includes exchanges, dark pools, trade reporting facilities, and banks. Now, FINRA is pretty good at processing the data, but we struggle with visualization. So if anyone knows how to plot billions of nodes onto a graph, please, I would like to talk to you. Let's jump into a technology, what technologies we apply to solve our graph problem that contains with billions of records. As I mentioned earlier, we use Hadoop and HBase, and we will go into kind of the data ingestion and access patterns that we have, and talk about how we designed our clusters to scale to that volume in Amazon. Before I go ahead and talk about HBase clusters, let me kind of give you a high-level overview of logical architecture. On the left-hand corner, you see FINRA Data Center. We are predominantly Netezza, Greenplum, and NASSHOP. And on the right-hand side, you see our VPC in AWS. What we're doing is our goal is to migrate 100% all our market regulation apps from our data centers into the cloud. And as part of doing that, we need to run in hybrid data centers. We need to make sure that data is being hydrated between the two clusters to allow us to run our processes on both environments until our in-house environment is retired. So we build a data bridge component that basically moves the data back and forth between two data centers, cloud and on-prem. Once data lands on S3, we have an encrypted buckets on S3. The data management picks up, which provides catalog registration of data, versioning of data, lineage, usage of the data, and cluster management. So basically what we're trying to do as part of our migration, we're trying to clean up our data. You know, as technology evolves, this is almost like a lifetime opportunity for us to take the data we have on-prem, to normalize it, ship it to the cloud, and register it so that we have an enterprise view of it. So once the data is loaded into the cloud, into S3, we have our persistent HBase clusters. We have 2 clusters running on EC2 nodes. We're on CDH 4.5, HBase 0.94, and we're using EC2 HS18 X large instances, which have 16 virtual CPUs, 117 megs of RAM, and 24 drives, 2 terabytes each. So let's kind of look at our ingest HBase. You know, how did we set up our HBase clusters? We have cluster A and cluster B. The cluster A is the traditional historical data store. It houses over 1 trillion records, and the ingestion to that cluster is bulk. Throughout the day, we process the graphs, and at the end of the day, we take that graph and move it into our historical data store. The access pattern for that particular cluster is 3. Given the event that happens on the marketplace, our analysts can look up for it and find the entire graph that part of event that event is part of. So on the right-hand side, our cluster B is, think of it as the operational data store. Throughout the day, events arrive to FINRA. It progressively builds the tree for that day, and it needs to look up its parent information because the parents may arrive at a later time. And it houses over 300 billion records, and as I mentioned, the ingest pattern is progressive. So let's dive into each use case and talk about what techniques we used to hydrate, to read and write the data from HBase. So just a background for that historical data warehouse. The first thing we had to do with that cluster is load data from the Greenplum. Remember, we're moving from our data centers into the cloud, and we have 2 petabytes of data sitting in Greenplum that needs to be back processed, put into the cloud, into an HBase. As part of doing that, we have to pre-create all these graphs. And a classical management problem, this needs to be done within time frame and a budget. Which really means is that we have to handle roughly 1 billion events in 24-hour period, which requires several millions of gets per second. And we had to run the process uninterrupted of loading that data, populating that historical data store 24/7 for 30 days straight. This is a massive data back process that needed to go into the cloud, and we had to finish within 30 days. We couldn't go longer due to our time constraints. So best practice, when you deal large volumes of data, we want to tell the regions to not split, so we want to control the splitting, which means that we have to evenly take our data and distribute between region servers. For that, we had to salt our primary key and take the data and kind of distribute between region servers. With respect to our put strategy, we decided not to go with put calls and do H-file bulk load. A classical sequence diagram of a put call. From the client, you go to the region server. From the region server, you go to a wall. And from region server, you go to the mem store. Then it flashes to H-file. Sorry, is there a question? The question is, we did a pre-split and we chose salting. Is that? Yeah. Sure. So the row key design is such that the algorithm takes into account, we take the primary key, we salt it, we put a salt in front of it. That allows us to basically distribute the data between ranges of regions. If you read Lars's book, he's talking about in his kind of the last chapter of the book, it's kind of a best practice to do when you deal with lots of data. So what we decided to do is go directly from the client to H-file, eliminate multiple and numerous flashes to control compactions. Because when you deal with large volumes of data, your compactions start kicking in. We needed predictability in our runs. We had to finish the project knowing that we can do this. So we went with basically H-file approach. So with respect to get or get list, the analogy I want to make is a classical grocery shopping list. Every time my wife gives me a grocery shopping list, the items appear in random order. She has no concept of grouping eggs, milk, and yogurt, so I can go to one aisle, grab everything. So my goal is to go to the store and quickly get out of that as fast as I can. So every time I tell her, can you just put those in the order so I can go to the right aisle, grab it, and not waste all these brute force RPC calls? She looks at me like I'm talking to an alien. So instead, what I do is mentally, I get the list from my wife. I can get milk, eggs, and yogurt going to aisle 1. I can get sugar and flour going to aisle 2, bread aisle 3, voila. I'm optimizing my RPC calls. So the strategy that we used is sorted partition batch gets. When you sort data, magic happens. And that reduced our RPC calls. Because we did not use the mem store to write to H files, we freed that memory to block cache. Remember with H file bulk loads? Let me just go quickly back. So here, we basically are not using mem store, so we did not allocate any memory to it. Instead, we gave all that memory to block cache, and we were able to get 90% block cache hit ratio. This strategy allowed us to get to several millions of gets per second. A classical access pattern, when an analyst looks at the event, they know the key. What it does is it gets the root primary key of that event. From the root primary key, it finds all the children of the tree. Now we can do a batch get. It gets all the data. Sorry, getting excited. For that tree and returns to analysts for them to kind of make analytical decisions. With respect to compactions, minors are always on, and major scheduled compactions are turned off in this use case. And minors would escalate to majors, but that's something we couldn't control. So let's go and dive into use case B. This is our cluster that sits in front and progressively builds the tree throughout the day. And it needs to look up its parent information, as you remember, because the parent of that node can come at a later time. What banks are doing and exchanges are doing, they're sending us the data, but the parent can come at a later time. So This particular process contains pretty complicated business rules. It includes data validation, relinking the tree as the data arrives, and identifies compliance issues, reporting of different firms not reporting consistently within our SLAs. And this is 24/6 operation. The put strategy is basically the same strategy in the reverse order as the get. Here, when the truck arrives at the store, grocery store, the store employee needs to put those elements, put those items into the shelves. So same approach, we're doing partitioning data prior to calling batch put. We're reducing number of RPC calls. And here, we're using the mem store and a black cache evenly. We're giving 50% for each. Okay. For this particular design, we're using scans. Tables are partitioned into daily and historical. We do scans on dailies. And one of the things that we've learned in the version of HBase that we're using, we had to switch from get to scan because we were retrieving millions of columns. These are, high-frequency traders. They generate pretty big trees daily, and that kind of blows up. And the latest version of HBase is handling that. With respect to compactions, this one is, we're running that every week. So we let the compactions run. So we got basically the two clusters loaded, our progressive cluster that processes data throughout the day, and historical cluster. So now we need to make sure that we don't fail. And we can handle the backups and DR. We're in production. So keep in mind we're running in Amazon, and we looked at the export snapshot of S3. Originally, it had some limitations. The three things that were not there that, with the help of Cloudera and industry and the S3 team, these tickets have been kind of addressed. Now we can store data in an encrypted bucket, where before that HBase export snapshots was not providing that functionality. We can remove we remove the expensive rename operation. S3 is not your classical file system, so every time you do a rename, it's not a simple pointer move. It's actually a copy and delete command. And if you're dealing with terabytes of data, that operation can be very expensive. We also supported, we had to go faster. We supported larger than 5 gigabytes upload. So we're able to finish the backing up every day into S3. So with respect to disaster recovery, we're leveraging AWS's infrastructure. AWS has a concept of regions. These are geographic regions. Within each geographic region, they have availability zones. Within availability zones, they have multiple data centers. So we have our hot cluster and warm cluster running in different availability zones. And we're backing up from our hot cluster to S3, as well as copying that data to another cluster in different availability zone. In case of failure, first we go to second cluster. If for some reason we can't get to it, we can always bring the data back from S3. S3 is a highly redundant, highly durable store. It has many replicas, throughout many data centers. And another thing we do is we copy data from S3 East region to West region for a cross-region redundancy. Some of the lessons learned running Hadoop on AWS. Hadoop is, I'm sorry, go ahead. Correct. Yes. Question was, do we have the same disaster recovery strategy for both clusters? And the answer is yes. So EMR versus Hadoop distro on EC2. Many people, they ask that question, when do you use one versus the other? EMR is predominantly for transient clusters, and it works really well with S3. Your classical Hadoop distro, think of it as persistent cluster. You're going to run that as a hosting kind of a solution, and it leverages HDFS, local disks, running HDFS on those disks. The EMR is easily auto-scalable, and you can scale up, scale down your nodes. The version of CDH we're using was not as automated, and I'm sure that the new products are coming and the new features are being implemented, and the distros are working on making it more scalable up and down in the cloud. EMR is well tuned out of the box, but not ideal for all use cases. With running your own Hadoop distro on EC2, you have much more flexibility in the customization. EMR works really well with batch access because the data is in S3. You fire up your Hadoop clusters and it just starts using S3 as your store. Hadoop distro works well with batch and interactive access because it's hitting the local disks on the servers. EMR supports pay-as-you-go model, and with Hadoop distro, because you're running persistent clusters, you might as well prepay for it. More lessons learned. We encrypted our S3 buckets for security reasons. We talked about eventual consistency, and actually we talked about S3 move being copy and delete command. So beware of that. If you're really trying to rename on S3 large files, that can take a long time. Because S3 is highly durable and available store, it has to copy all that data, and there's an eventual consistency issue there. If you're writing it, it may not have propagated to all the nodes that it needs to write if you're accessing the wrong bucket or the bucket that hasn't been copied to. We encrypted our local disks, and beware of local disk warming concept. This is AWS's concept. When you ask for a node from them, before they can give it to you, they wipe it clean so that you don't get the data from the other tenant. So that can impact your first run of performance. After that, your performance becomes more predictable. We're using placement groups. This guarantees us high network between the nodes. If you don't do that, because of HBase kind of chattiness, the performance can suffer. So with respect to cluster sizing, in a traditional data center, you got to worry about 4 things: CPU, memory, I/O, and network. In AWS, you get what you get from a network. And given our use cases, actually, the memory and CPU, the combination of that, basically we had to worry about 2 things: memory and CPU 1, and the I/O 2. And they have multiple instance types, so you really need to run your tests to figure out what your access patterns are and ingest patterns are and what the best configuration is. And the price can really vary if you choose one instance type versus the other instance type. We're working closely with AWS, and they are basically, based on our use cases, they are developing new instance types and storage types. So what's next? Hadoop has been proven technology that runs on hard iron and on the data centers. We're breaking the barrier. We want to make sure that Hadoop is a world-class citizen running in the cloud. So we're working closely with Cloudera, with AWS, and other cloud providers to make sure that capability is there. The big data management component, which is a topic for a next discussion, when we see each other, we'd like to talk about how we're managing our data in the cloud, the services that we've built in terms of cataloging the data, the cluster management, as well as lineage, where it came from and where that data is being used. That's something that we're investing heavily. And as well as we're looking into, now we're getting very comfortable with processing data. We're spending a lot of energy into advanced analytics. So we hope when next time we see each other, we discuss those items. So that's the end of my presentation, and I hope you found it interesting, and I'd like to open the floor for any questions you might have. Yes? I'm afraid I won't be able to go into those details but if there is any specific question, we can take it offline and talk about it. There's a lot of interesting stuff we do for performance reasons, and we're in competition with other companies. So I'm sorry, I can't disclose that information. That's also something I'm not allowed to talk about, but these are great questions, guys. So, I'm sorry. How big is our cluster in AWS? That gets into our price point, and as I mentioned, at this point we're not comfortable discussing those. Yes, sir. How much time does it take from data ingestion all the way to finding fraud? It's a great question. What we're doing is we're ingesting data throughout the day. The data comes to us, in chunks from banks and exchanges. We build the graph as the data arrives. What we have is we have a suite of surveillances and algorithms that's run on top of that data, and that process can take up to a few days to run. It's not as near real time. If that answers your question. Let's go back in the back room. Yes. I'm sorry, I can't hear you.
What went into the decision to pick AWS versus bare metal? Did you ever reach a point where AWS got too expensive and it thought of the break?
So what decisions went into choosing our infrastructure cloud versus on-prem? The nature of the work that we do is very dynamic. We ask a lot of what-if questions. Events can happen, and we can go back and say, rerun all these algorithms against this data and spin up all these clusters and then tear them down because we don't need that anymore. So that elasticity of cloud is very attractive for us, and it proves to be very valuable. Instead, we would have had to buy all these servers and really size it where we all run and then keep on adding servers when we need to, and then taking them out is kind of difficult. Instead, we're treating that as a commodity and saying, AWS, run this for us. We want to run our business on top of you. You manage the infrastructure. Yes, sir.
How do you manage workload automation? Is it Uzi?
How do we manage workload automation? We leverage heavily, we build a data management component, which has the workflow component in there. We leverage AWS's notification systems. When data arrive, the workflow picks up, and it moves to the buckets, kicks up the clusters, move the data, run the surveillance engine. So we build our own using workflow engine.
Just to add on to that question.
Yes.
Was it intentional for you guys to build it, or you tried to work closely?
We tried Uzi, we tried different things. We found that, we're using an open source stack. I forgot what activity workflow on top of that. So we're leveraging that as well as other open source libraries. It's not custom. So actually, our plan is to open source that very soon. Yes, sir.
Is the data in the offline store always coming from the legacy greenplum system, or is there a point where you start to get up your online store?
Yeah, so the question is the data coming from offline store continuously hydrating the cluster in the cloud? The answer is no. We've done that. We've finished, and that particular piece can be retired once everything else, all the dependencies on our on-prem go away. So now we're operational in the cloud since May of 2014. Yes, sir. Do we use any graph processing tool? No, we're leveraging HBase for that. So in the past, we've tried different things. Our knowledge of HBase and the MapReduce and the requirements that we had about constantly changing the graph, led us to go with an HBase solution. Yes, in the back. Which use case? All right, so it's roughly 120 regions per region server. Yeah. Yeah, for first use case, obviously, yeah. Can we switch? Yeah, okay, go ahead. So it takes basically, we copied the data to a warm cluster, so it's there. We bring it up within less than an hour. So if we need to copy the data from S3 back, that can take several hours because, again, it's petabytes of data, and obviously it's compressed and things like that, but there's laws of physics now play when you need to go multiple threads, bring it from S3 and hydrate it, the cluster. Yep. Yes.
There are stores that are designed for graph. Do you guys have a process where you look like a review really or something else better than HBase?
So there are graph stores and tools that are out there on the market, and have we looked at those before making an HBase decision? Oh, next iteration, will we look at those? Yes, the technology changes so fast. If we find something better, we're looking heavily, instead of doing MapReduce, going into Spark. We want to look at streaming. We're pushing the industry to start sending us data via streams. So there's a lot of innovation is happening. And, frankly, when we're at AWS, they innovate pretty fast. So we don't have to worry about the servers and purchase orders of buying stuff. So we focus on kind of our business problems. All right, so thank you very much. Appreciate it, guys.